Welcome to my presentation entitled Classifying Urban Building Footprints into Residential, Non-Residential Categories in Low-Income Settings. Thanks for coming. My name is Lloyd. I'm a research fellow in GIS at the University of Southampton. I work for the WorldPop project. We aim to provide open access spatial demographic data sets to support a variety of applications, mainly to do with international development, that kind of thing. As I say, I'm a GIS person. I'm not a population analyst, despite the fact I work for WorldPop. I'm not a statistician either. That's just a disclaimer for what will follow. But as part of the GRID3 project, which is one of the big projects we're working on at the moment with project partners, for the last 12 to 18 months, I've been taking an interest in settlement modelling in collaboration with Hugh Sturrock at the University of California. And I've been using his settlement classification model with newly available building footprint and label data in new settings. So that's, in this case, it's two of our GRID3 countries which we're involved with and we're in country with at the moment. That's the Democratic Republic of the Congo and Nigeria. Now, in the process of that, necessarily I've had to create extensive new GIS workflow, which is kind of the unique aspect of the work, the selling point, if you like, which I'm promoting here at this presentation and will be publishing a paper on shortly. This GIS workflow enables a broader range of data to be input to the model, and this is important to allow future researchers to access and to use the model as new building footprint, label, and impervious surface data become available in these low-income settings. So why classify settlement? Well, arguably, the best way to inform population models is to include urban settlement data or proxies. The mapping of building use is frequently inadequate. There's a lack of completeness and attribute accuracy, although particularly with the completeness, with the latest data that's coming through now, it is getting a lot better. The attribute accuracy still lacks somewhat. The distinction of residential from non-residential buildings via machine learning provides a much needed alternative to time-consuming and labour-intensive fieldwork. So what approach are we using? Well, we're using the SuperLearner package in R, which was designed by Poly, and we are using an object-based stacked generalization ensemble binary classification machine learning approach. Lots of words there, but basically that's the approach of Hugh Sturrock. I'll explain what some of those words mean in a minute. Basically, buildings in urban areas are classified according to whether they're either residential or non-residential, and the model is trained and tested to predict on all urban areas within the Democratic Republic of the Congo and all urban areas within Nigeria. So the SuperLearner algorithm uses cross-validation to estimate performance of multiple machine learning models, or base learners. We call all the individual models base learners, and then we stack the base learners and weigh them, producing an average ensemble after assessing the performance using the test data. The ensemble can then predict on larger data sets, in this case, buildings with no labels per each country. So this is the Sturrock paper for those interested. This describes the model that's used. Though, as I say, there will be a forthcoming paper describing the GIS workflow that I'm presenting here and describing the application of the new data in these new case study countries. So in terms of the software that we use, it's all open source. The GIS workflow to get data into the model is performed at command line. It's a semi-automated workflow. We use Windows batch files or the Linux equivalent. The modelling is undertaken on the University of Southampton Iridis high-performance computing network, as are some of the more computationally expensive GIS workflow, but otherwise the GIS workflow is performed locally on a local machine. Either way, there's a semi-automated GDAL script, of which various other scripts perform tasks, be they Python scripts or spatial light or grass. So the source input that goes into the model, there's the Maxar, the vector polygon Maxar technologies building footprint data, similarly OSM building footprints and the attribute labels that go with those. And we also have additional attribute labels that we've gathered from manually filled map building structure labels from the World Bank, from Oak Ridge National Laboratory, and from the University of California. So this is a picture of the building footprints. This is one of the better examples of OSM completeness in low-income countries. It shows how the Maxar data is basically a game changer. This is one of the better examples of OSM coverage, completeness, should I say, of the data. That's shown in blue. The Maxar data obviously provides a lot more coverage, as you can see. The Maxar data, the footprint data is extracted from satellite imagery directly. Vector label label inputs. This shows the distribution of OSM and other structure label data for the two countries. Green dots represent residential, red dots represent the non-residential structures. The data labels are available throughout both countries. The distribution is good in the urban centres, as you can see. The other source data sets that we use as input to the GIS workflow are the GMIS impervious surface raster data, that's the NASA data, and we also have the OSM highway data for January 2020, which is input directly into the model without any processing being necessary. I'll skip over the source data limitations because of time. The GIS workflow. Just bear with me a second. Right, so the input data sets to the workflow are denoted in grey on this diagram. The GIS workflow processes are shown in blue. The inputs to the model are denoted in green, and the model is denoted in red with the outputs in black. This is a whistle-stop tour of the workflow. I apologise for that, but it's due to time. So the building footprint data are then merged into one. Non-OSM building labels, they're merged and simplified into a single data set, and then because we're uncertain about the non-OSM label positions, there is a level of uncertainty about that. We perform a moving 5x5 pixel window on a rasterized version of the data in order to average that out. And then we can convert that back to points and then convert that to a polygon layer, which indicates the residential zones. The 5x5 pixel window averaging operation is sensitivity tested, so we pick a sensible value for the window size. And the residential zones have certainty at that given window size, but with that caveat that those zones are residential. So then we use those residential zones to append residential attributes to the building footprint data. So we end up with a building footprint data set which includes the OSM and the non-OSM labels. Those building footprint data are then input to the model. We also then take those building footprints and we do another area of GIS workflow, which combined with the impervious surface data allows us to create two impervious surface tabular inputs to the model. One of those has the building identifiers for each individual building and impervious surface values for the centre of each building, and the other has the building footprint IDs and the impervious surface value in an average in a window around each building. So we end up with the building footprint data as an input to the model. We end up with the two tabular impervious surface inputs to the model, and we end up with the highway data, which goes straight into the model without any processing. So then we can predict whether buildings are residential or not. We do this by training the model with 90% of the label building footprint data, and we use the other 10% to test to validate the model to see how well it's performing, which means we have model statistics, such as the AUC value, which tells us how well the model's performing. It also means that then we can predict for the buildings which don't have labels. We use the random forest and the extreme gradient boosting base learners. We tried other base learners, but they persistently weighted to 0 in the output, so we skipped them. So the data input to the model allows the calculation of various model predictor variables such as building area, distance to nearest road, urbanicity, that kind of thing. I won't go into that in too much detail. So this is a structure of the summary of the building structure data. This just gives you an idea of the sort of numbers that we've got of buildings in the data set. So for the Democratic Republic of the Congo, we've got about nearly 3 million buildings without labels and about 11.5 million buildings for Nigeria. But there's 100,000 buildings with labels for the Democratic Republic of the Congo, but only about 17,000 for Nigeria. So you can see that proportionally, relatively speaking, the Democratic Republic of the Congo has a lot better representation of labels relative to Nigeria, and that is reflected in the success of the modelling. As we see, when the performance of the superlearner model when applied to the test data for the Democratic Republic of the Congo, nearly 93% of non-residential and residential buildings are correctly classified. In Nigeria, that drops to about 85 point something for both. But nevertheless, that's still a good enough value. And we have an AUC value of 0.98 for Congo and 0.93 for Nigeria, which is excellent for both. And the output predictions, the actual predicted values for buildings in the non-labeled data, in excess of 92% of structures for the Congo and in excess of 95% of structures for Nigeria are predicted to be residential. When we visualize that seems very sensible. Visualize the output predictions. The sample for Kaduna in Nigeria the green buildings are residential, the red buildings are non-residential, and you can see very clearly that the industrial buildings are very clearly delineated here and here and there, and particularly here as well, as are the residential areas. And so at neighbourhood scale, it looks very very successful. In fact, obviously, but models never are, and data inputs never are. But if we scrutinise it a little bit more, and we go down to choose another example, and we go down to street scale. This is an example from Lubumbashi in Democratic Republic of the Congo. This is a city that's in the southeast of the country. An example suburban locality at street scale. You can see that most of these buildings, if not all, should be not necessarily all, but certainly most of these buildings should be residential. And it does appear as if there are some misclassifications, despite the excellent statistical performance of the model. I would suggest that these misclassifications may be due to unusual heterogeneity of building structures relative to the rest of the country, and or to do with limited training data within specific localities, within this specific locality. I would say that in this case, it's probably down to the latter, limited training data, having looked at the data, although there is an even distribution of training data around the country, and there's good representation for Lubumbashi. In this particular suburb, it is a bit lacking. And so I reckon if we throw data at this, if we get more training data in it, ultimately, it may well resolve this problem of its own accord. But that's for the future. And that leads me nicely to closing statements, which is basically that we should explore use of the model in the future. In terms of developing the model in the future, we should explore use of the model with new data in new low-income settings as data becomes available, and in the existing settings as new data becomes available, as I said. And we should further explore how variation in the window size affects the model output, especially when other parameters of the model are altered. I'll skip that one for brevity. But these are the big main future developments. We need to modify and expand the classification algorithm to include a greater range of appropriate data inputs and predictor variables in order to improve predictive power. Things we could do, there's new data coming out now to do with building heights. There are certain cities in low-income settings where there's building height data starting to become available. That could be very useful in future modelling. There is also a colleague of mine is working on patches of urban form. That's mapping. That's where map footprints are treated as patches in the landscape, and a variety of metrics are used to quantify the morphological patterns. That could be useful as well in terms of defining things a little better. And also, we could take something like individual characteristics from census data, if we can find it for individual countries, such as rooftop type. That might be useful in making a more effective classification. But the bottom line is, at the end of the day, we want to adapt the model a bit more to classify a wider variety of building function in order to better inform the population model. So instead of it just being a binary residential, non-residential, we want to be able to identify mixed-use buildings and informal settlements, most importantly. So I would direct people to the Grid3 website and the WillPop website, please do. And as I say, there will be a paper coming out in the next few months, which details this work in much more detail. Thank you.
Thank you, Christopher, for your great presentation. Perfect timing. Thank you. Okay. And some question. Colleagues, good talk. I would like to know how to factor mixed needs uses, residential, commercial, which is rather a common phenomenon in developing cities.
Yeah, that's a good question. In this instance, I'm aware that some people exclude mixed use from these sorts of models to create sort of clarity between the differentiation between the residential and the commercial land use. I didn't. I lumped mixed use in with residential, which might have weakened the classification. I don't know, but as far as I was concerned, I was looking for classifying residential properties as a priority. So mixed use is obviously residential as well. So I put the two together. It's an entirely subjective decision, but yes, the results are as they are. So.
Okay. The next question, really interesting stuff. Do you have more info or a pointer for the work and urban form you mentioned towards the end of the talk?
On the urban form, I'm not sure what you mean by that, actually.
Danny, explain more. Okay, we go to the next question.
Sorry.
Okay. Yeah. It's a long question. First.
I'm with you. Sorry, I'm with you. Sorry, no, I'm with you. I don't have more information on that at the moment. But as I say, a colleague of mine has been working on that, and he's just produced a paper. It's Chris Josham. Hang on. Just bear with me. I'll type this in.
Then it says, in the last slide, you had mention of patchiness and urban form.
Sorry, please go on.
In the last slide, of patchiness and urban form.
Yes, yes, absolutely. It's the Chris Josham et al. Paper 2020. I've just typed it into the chat. That should clarify.
Okay. The next question is from Anna. Wouldn't work more reliable if you start somewhere with accurate building data first before going to developing parts of the world? And the second question is also, how handle the uncertainty? For example, inconsistency between Maxar building and OSM building before merging, or lack of the tag labels in your evaluations. And the last question is, up to what level this match against population estimation of word pop, considering the approximation occupancy?
Okay. Yes, in terms of the first question, I did skip over. That was one of the future areas for future work. Actually, I did skip over that for reasons of time. But I have done some work in terms of looking at use of some of the better building footprint data and label data. I've used some of the Bing data for the US, and I've modelled that. If I put that through the model and looked at predicting for areas in DRC and Nigeria using that data. I couldn't even say limited success with that. It was that it's tough to do. It's in principle, it's definitely something I want to investigate further in the future. As it stands, I've looked at it and it hasn't worked yet. But I agree. It looks like it should be. In principle, it looks like it should be a promising thing to do. So that's the answer to the first question. How handle the uncertainty between Maxar buildings and OSM buildings, or lack of text? Inconsistency between Maxar buildings and OSM. Yeah, well, essentially, when the merge operation takes place in the GIS workflow, we perform that using a disjoint operation, which basically means that we don't just merge the two data sets together. Wherever the Maxar data intersects the OSM data, we eliminate the Maxar data. So there's never any overlap. So we're merging the OSM buildings, which frankly are better delineated, we find, with the remaining Maxar data in order to complete the data set out. That's how we sort of merge the two together and successfully. In terms of the labels, obviously we in merging the labels onto the buildings, we are adding. We're improving the attribute information on the building footprint data set, and that's obviously the point of the exercise. Yes, and in terms of question 3, up to what level these match against population estimation? To be honest, question number 3. That's not something I've looked at. That's not actually my area. I say I'm a GIS guy. I'm not a population analyst. But that would be one for my colleagues, I think. Question for my colleagues.
Okay, thank you, Christopher. The next question is, what about the slump detection? Any insight you have?
None as yet, no. A limitation of this is that, unfortunately, because we're using the impervious surface data and we wanted to use data that was had as complete coverage as possible, because if we use this method and apply it to different countries, we want to be having consistent impervious surface data. We were choosing completeness of the impervious data, surface data coverage, if you like, across multiple countries, as opposed to up-to-date impervious surface data. So that means that inevitably we're probably missing out on certain slum areas, because basically the model will discount any areas, any buildings that fall outside of the impervious surface data set. So it's not so good at the moment for slum detection, unfortunately. And of course, we still need to develop the model, as I say, to incorporate these extra non-binary detections. So that's something for the future. But yes, it's certainly on our radar, because it's obviously an important thing.